Hi, in this video I will go through extracting orbitals of any level of energy. We know for any orbital we need to have three quantum numbers. The first one is n, or principal quantum number. Principal quantum number. And this one, it will show you distance of electron from nucleus. If you increase n to n equal 2, size of orbital will be bigger. So R2 will be bigger than R1. So as we increase n, and as n is going up, size also is going up. Second quantum number that we use for any orbital is angular momentum quantum number, or L. Angular momentum quantum number. L is equal to 0 to n minus 1. L will tell you shape of one orbital. And when L is equal 0, we say it's s orbital. L equal 1 is a p orbital. L equal 2, we are dealing with d orbital. And when L is equal 3 orbital, it's a f orbital. Last quantum number that we need for any orbital is direction of that orbital. We say it through ml, or magnetic quantum number. ml is minus L to 0 to plus L. I'm gonna go through N1, N2, and N3, and I will show you all the possible orbitals for any level of energy. And I start with N equal 1. N equal 1. When N is equal 1, L will be 0 to n minus 1. So L will be 0 to 1 minus 1. So we are dealing with just 0. We said when L is equal 0, when L is equal 0 is a s orbital. So we have only s orbital. Name that orbital. It's gonna be 1s. 1 is for n equal 1, and s for L equal 0. How many directions for 1s orbital we have? You can get that one through ml. ml is minus L to 0 to plus L. ml is gonna be minus 0, which is equal to 0, or plus 0 equal to 0. So there is only one orbital, one direction for s orbital, and s orbital is a spherical orbital. So there is no really specific direction because it's a spherical orbital. Now, I need to tell you something, we call it node. because I need to show phase of each orbital. Node is a place that's probability of finding electron is equal 0. That means Schrödinger equation has answer of 0. Total number of nodes is equal to n minus 1. We have two types of nodes. One of them is angular, that's equal to angular node equal to L, and the second is radial node is equal to n minus 1 total minus L, whatever we use for angular node. So when we are speaking about 1s orbital, total nodes will be n minus 1. It will be 1 minus 1, 0. So we don't have any node. We don't have any radial or angular node. Just give it positive sign, and that's it. We're done with 1s orbital. Now I want to show radial distribution for this orbital. Radial distribution, it will tell you if you move in any direction, what's the probability of finding electron in that specific r or distance. The way we show the radial distribution, we put distance versus probability or psi 2. Again, probability of finding electron. So that is a probability, and here we have R. Move in one direction from the nucleus, move in any direction you want. We start from the nucleus, so there is no chance to find electrons, so you have to start from 0. And when you move left, right, or any side, you start to increase probability of finding electron. So the probability of finding electron is going up, and then again it will go down until you reach end of orbital. Here in that area there is no chance to find electron. Now you want to find number of radial nodes. We know for 1s orbital we don't have node because there is no node. One easy way to find number of radial nodes, cover initial point, which is the nucleus, and the last point, which is end of the orbital, and see how many times this graph is crossing the horizontal line. In this case, 0. That means we don't have a radial node for 1s orbital. Now I go through n equal 2. N equal 2 gives you L equal 0 to n minus 1, L 0 to 2 minus 1. So we have two answers, 0 and 1. When is 0 is a s orbital, when is 1 is a p orbital. Go with first case, that is n is equal 2 and L is equal 0, which is s orbital. Total nodes. is gonna be n minus 1, 2 minus 1, 1. So we have one node. Find angular and radial node. Angular node will be equal to L. When L is equal 0, you don't have angular node. Radial node will be total n minus 1 minus L. So it will be 2 minus 1 minus 0. There is one radial node. ML minus L to 0 to plus L. If L is equal 0, so ML it will be equal 0. And we know S orbital is a spherical orbital. It doesn't have specific direction. So I'm going to show 2s orbital next page. So we have 2s orbital n equal 2, so I will write 2s L equals 0, which is equal to S. So I'm dealing with 2s orbital. I have one radial node. So we said one radial node equal 1. The total node equal 1. And there is no angular node. The way you show radial node, show it as a circle but with dot lines. We have one nodal surface. That nodal surface will change sign of the phase from positive to negative or negative to positive. Start with one sign. Say for example positive. Positive. When you reach the node, turn to negative. Here you have positive, you pass the first node, it will be negative. Radial distribution, psi 2 or probability, and here are start from nucleus, move one direction, start to build some probability until you reach the first node. So this one is the first node. And then you go inside bigger area. Because it's a bigger area, you have to show it with bigger spectrum or peak. Now I need to find number of radial nodes. I know I have only one, but the way we can figure it through the graph, I will cover initial point and last point. There's one crossing point. This line is crossing the horizontal only one time, so I have only one node, one radial node. I should say one radial node. So we're fine. So the graph is completely correct. We said when n is equal to L is gonna be 0 and 1. We did the work for 2s orbital. Now I go through 2p orbital. N equal 2, L we got it 0 and 1. That's it, S and P. We did the work for S, so case 2 will be N equals 2, L equal 1 is a P orbital. And total node will be equal to n minus 1. 2 minus 1, 1 node. This time L is not 0, so you do have angular node. Equal 1 or equal L. And radial node will be the total n minus 1 minus L. And it will be 2 minus 1 minus L, which is 1. L equal 1. So there is no radial node. You are dealing with a p orbital. Here is p orbital. Show the all the nodes. First node we have that's an angular node. In this case, because n is just 2, we have only one node, so the only node we have is going to be just angular node. And you start with, again, one sign, say this one is negative. When you reach the angular node or any node, sign will be opposite. So from negative we turn it to positive. Radial distribution. Move in any direction, anyone you want, from center to up or down. Beginning, you don't have any probability, so it will be 0. And second you move inside, this lobe, or you leave the nucleus, start to build probability, so it will go up, then again goes down until you reach end of orbital, where we don't have probability. We don't have radial node, so if I cover initial last point, I don't see any crossing point, and there is no crossing. So there is no radial node. Last thing I need to say about 2p orbital is magnetic quantum number. For n equal to L equal 1, because L is equal 1, ML will be minus L to 0 to plus L. L is 1, so you will have minus 1, 0, and plus 1. We have 3 answers for L equal 1. That means we have 3 directions. I will show them as X, Y, and Z. There is no connection between minus and X, or 0 and Y, or plus 1 and Z. Okay. Now we will go through n equal 3. When n is equal 3, possible answer for L, it will be 0 to n minus 1. It will be 0 to 3 minus 1. I'll have 0, 1, and 2. First one is S orbital, second P, and third one D. Similar to n equal 2, I go with first case. First case, n is equal 3, L equal 0, so it's a S orbital. Total nodes will be n minus 1. 3 minus 1, 2. So when n is equal 3, totally I have 2 nodes. but depends to L, you can have angular node or not. For instance, in this case, because L is equal 0, we don't have angular node, and whatever we have as a node will be radial node.
It's 6 o'clock.
So we have two radial nodes, ML minus L to 0 to plus L, so there is no direction. It's just a spherical orbital. I'm dealing with n equal 3 and s orbital. So here's spherical orbital, n equal 3, write it, is a s orbital, so write 3s. You have two radial nodes, show them by dot circle, first one, and that is the second. Change the sign anytime you cross the node. So I start with positive. I'm passing first radial node, sign will be negative. When you pass the second one, it will be positive. Radial distribution. Move in one direction, any direction you want. Say we are moving this direction. From the nucleus, there is no chance to find electrons, so probability will be 0. But when you go inside this area, smallest one, you will have chance to find electron until you reach the first node. So this one is the first node. And now we are there. If I pass the node, I get chance to find electron. The area is bigger, chance is bigger, so you show it with bigger peak. Now I reach the second node. So this one is the second node. Again, I pass the node, faced with bigger area, show it by bigger peak. Cover initial and last point. You have two crossing areas, two crossing points. Those are your radial nodes. Second case, n equal 3, L equal 1. You are dealing with p orbital, and you know the total nodes is going to be n minus 1, so 3 minus 1, you are dealing with 2 nodes. Angular node equal L. L is equal 1, so you do have one angular node. Radial it will be total minus L. 3 minus 1 minus 1. You have one radial node. ML minus L to 0 to plus L. So it will be minus 1, because L is equal 1, to 0, then you add 1 unit to 0, it will be plus 1. have three directions: X, Y, Z. Another way, you're dealing with 3p orbital, but you can have px, py, and pz. So 3p orbital, and because I have three answers for ML or magnetic quantum number, I need to have three directions. So this one will be the first, or p orbital is going to be 3px, 3py, and 3pz. But they have same level of inertia. Okay, so we are dealing with p orbital. Is p orbital is a 3p orbital. We have one angular node, and we have one radial node. Start with one sign, positive. You reach the first radial node, negative, and then you reach the first angular node, negative, turn to positive, and other side of radial node, it will turn the positive to negative. Radial distribution. Move in one direction. We have the nucleus. There is zero chance to find it. You go inside the first area, and now there is chance to find electron. Show it by one peak, small peak. Now there, that's the first node, first radial node. Then you pass the node, you build bigger area to show that there is more chance to find the electron. So any electron in a 3p orbital is hanging around this distance. Cover initial point and last point. As you see, there is one crossing point, so there is one radial node, and that's true. And last orbital from n equal 3 is n equal 3, L equal 2. We are dealing with d orbital, and we know total node equal to n minus 1 will be 3 minus 1, 2 nodes. Angular node is equal to L. L is equal to, so we have 2 angular nodes. Total we have 2 nodes, so we don't have radial node. ML minus L to 0 to plus L. L is 2. The way you draw any d orbital, choose one, plane. First, in this case, I go with Z and X. Put two lobes between the axes. Same thing here. And apply all the nodes you have. You have two angular nodes. One is going to be here. That's the first angular node, and the second two will be there. Now start with given sign to one of the lobes. For example, positive. Positive sign we turn to negative by this angular node. Negative will be positive by that node, and positive will be negative. Radial distribution for this orbital. Just go in one direction. Start from 0. You go up, then until you reach last point where there is no chance to find electron. The plane I use is XZ. L is equal 2, N is equal 3. So I'm dealing with d orbital from third layer. So I will the way we write the name of orbital, you write N, write D, and plane of orbital as a subscript. So the orbital will be 3D XZ. If you change the plane, for instance, to XY, orbital it will be 3D XY. Or you can do it also for YZ. X, Y. Oh, yeah. For instance, X, Y, or go with X, Z, Y, Z. Positive, positive, negative, negative. Plane I'm using is XY, so orbital will be XY from third layer. And this time I'm changing the plane. Plane it will be 3D XZ. Positive, positive, negative, negative. Positive, positive, negative, negative. It's a 3D orbital and the plane is YZ. Another 2D orbital. If you go with, say, X, Y, or you can put X here, Y there, it doesn't matter. And when you put the lobe exactly line with the axis, in order to make difference between this orbital, which is a 3D and it has same plane of xy, which is same as first orbital. Way we write name of this orbital, we put subscript of x square minus y square, because I want to say that this orbital is different than dxy. Dxy. They are using same plane, but you want to show that this case lobes are sitting on the axis, not between them. Sign, you go positive, positive, and this one negative, negative. And the last orbital is a dz square. P orbital, and you apply one ring. Give it positive, positive, and inside that ring negative, negative. And here we have the z, call it dz square.